We'll give the others an extra minute, 2 minutes to join. So we'll start at 11:02.
Yeah, that's fine with me. Thanks.
Okay, good morning, everyone, and welcome to our session this morning. This is part of the Spatial Stats seminar, or the Spatial Stats group, which is part of SASA, the South African Statistical Association. Inga is the chairperson of this group, but she would not be able to attend today. She has other commitments. And Renata and I also am helping Inga manage the group as well. So today our presentation is by Dr. Innocent Maposa. And Dr. Innocent Maposa, he is a researcher and a senior researcher in the biostats at Stellenbosch University. That's in the Department of Global Health Division of Epidemiology and Biostats. He also has an appointment with the Division of Epidemiology and Biostats, a School of Public Health at Wits University. He has several publications in spatial stats on infectious disease modeling, public health, and clinical epidemiology as well. Dr. Maposa completed his PhD in statistics from the University of Western Cape in 2017, then went on to work as a consulting biostatistician and a senior lecturer at Wits University before joining Stellenbosch University. He has MSc and honors in biostatistics from the University of Zimbabwe, as well as a double major in maths and stats. Besides his academic involvement, Dr. Maposa also consults for research institutions and centers. Today, Dr. Maposa is going to give a presentation on spatial methods and applications. So I would hand it over to him to do his presentation and also introduce his topic as well. Thanks very much, and thanks, Dr. Maposa, for agreeing to be part of this spatial stats group and giving a presentation as well. Okay, I'm going to mute myself. So you can go ahead, Dr. Maposa.
Thank you, Pravesh, Prof. Pravesh, and your team for giving me the opportunity to share some of the work that I've been doing within the spatial kind of analysis space. Yeah, so I will just go through the concepts around which my studies have been going around, which is spatial methods and the applications in epidemiology, basically. Yeah, thanks for the introduction again. And I wouldn't want to add anything more to that. But let me just maybe switch off the video and then speak through the talk that I have. Yeah, so thank you very much. All right. Okay, so basically the discussion we're going to have today is going to follow this kind of structure. We are going to just look at some basic background kind of aspects and then some spatial epidemiology kind of thoughts, and then the spatial modeling, and then the applications, which may then include the joint spatial modeling and then references and so forth. So these are not going to be in-depth kind of aspects, but they're going to be a prelude of just the concepts that I'm going to then share later in terms of the applications. So to give that background, to the applications that I've been doing. Basically, in addition to the introduction that has been given, just to highlight that I'm also a member of the International Biometric Society, where I serve also as an IBS representative committee member, representing the South African region. And within that committee, there are different subcommittees, and I serve in one of the task force, which is the Young Statistician Showcase Award Task Force, and I'm chairing that task force. Where currently, actually, we're going through some abstracts and so forth, the papers from some applicants, young statisticians who are vying to get this particular award, travel award. Maybe I can take this opportunity also to encourage, our community, our students, PhDs, and even postdocs and so forth, to kind of, become members of IBS, and then they will be eligible for this type of an award. Then I'm also a member of the of SASA and SAMSA, that is the Southern African kind of Mathematical Sciences Association. So I joined this SASA recently. Of course, I've attended some conferences in the previous years, I think one or two, but this year I became a member. Yeah, thanks again to the team for the invitation. Then I'm also with Stellenbosch, and yeah, currently. So in terms of the work that I've been doing, that I've been doing with some colleagues, with some collaborators. Generally, we have been working within R, and there are packages that we have been using basically for most of the work that we have been doing around spatial methods and their applications, and those includes INLA, which is an approximation kind of Bayesian method, that can approximate the posterior distribution for this kind of models, high dimensional kind of posterior densities. And then we also kind of use this, the R2 base X and then R2 Winbargs, and then the SP depth, SF, GG plot, and SP kind of packages, and yeah, so there are quite a number of other packages that we use, including the ArcGIS in R as well. So why spatial analysis? I'm sure most of you would already be familiar with some of the reasons, but I will just kind of reiterate from the perspective of the applications that we've been doing. So in recent years, there's been basically a deluge of or an explosive growth in terms of spatial data, and their spatial, their widespread use, of the different databases that are available with these spatial kind of data. For example, my main resource for data has been, the demographic health surveys, that is DHS kind of data sets. And from a few years back, they started to also collect data, within this, with spatial attributes. And that has helped actually to understand certain conditions, certain diseases within their spatial context. So there are basically some specific features of geographical data that preclude basically the use of general purpose kind of data handling methods. And some of the elements or aspects include the spatial relationships among the variables. This can be the outcome variables, or this can be the explanatory variables. In other words, some explanatory variables might have what we may call, heterogeneous effects on the outcomes, depending on the location, on the right, depending on the location where the measurement has been made. Then we have the spatial structure of the errors. In other words, because of heterogeneity as well, some covariates may not capture, the effects in another particular area. And what that means is that the residual kind of effects that remain unexplained in those particular areas, they will then be added to they'll be added to the errors or to the error terms. So at the end of the day, you end up having some structure, some spatial structure, of the error terms. So observations that are not independent, because if there is clustering, at a local area, then the observations within that particular local area cease to be independent and identically distributed, of which, in most of the maximum likelihood kind of best methods that we generally use, you would notice that we make an assumption that they are the random variables in this particular context are IID, which in this particular cases might not be optimal. So there is also spatial autocorrelation that exists with the geographical data. And then there are also some nonlinear kind of interactions in the feature spaces. So all these particular, aspects, they won't be captured basically from our classical approach, in analysis. Right. So the classical statistical methods then perform a little bit poorly with data, that is this particular spatial structure. And the data, this type of data has two attributes, basically. So there's the non-spatial element and then the spatial kind of attributes. So all these elements, they need to be captured in order to get a full understanding of the data generating process, in order to either make interventions or make recommendations or well-informed kind of conclusions. So in terms of the spatial data, so there are different types, and of course I won't be going into the details with these data, but I will highlight the one that we have mainly used in the different studies that I have been involved in. So when it comes to vector type of data, spatial data, there are points, there are lines, and then with points, in other words, you're looking at measuring a particular individual at a particular location, where you can have their latitude and longitude kind of values at a particular position. So like in most of the surveys nowadays, in the surveillance kind of study sites, they normally have data collectors go to a particular place, and then they with RedCap you can get the location of the individual, and their information can be tied to that location, to their XY kind of coordinate. And with this data, you can further process it in terms of analysis to then see where there are more cases, of a particular condition that could be TB, for example, looking these spatial points. But for DHS kind of surveys and so forth, and other surveys, for ethical reasons, there is always some kind of buffer in terms of a distance, from where the actual measurement has been made. So sometimes that makes it a bit complicated to then work with this targeting a specific outcome at a particular position. Especially when the data is, when more people have been measured within a particular area. But then there is also lines, which includes the roads, the streams, and so forth. That's also part of, vector type of data, but I rarely kind of use that. What I have been using mostly is basically the neighborhood or the boundaries kind of type of vector data, which is basically comes in terms of area or kind of data. So in other words, if you have a district, that's an area, and that district has got boundaries, and everyone within that particular district can contribute, to this particular, boundary, or so you can then do your analysis based on these, boundaries. So the beauty of this is that when it comes to the DHS, in most countries, they have actually aligned these demarcations with the data that they collect, so that you can easily merge the shapefile that comes with the the projections for these particular locations, to the non-spatial kind of data that you have, and then you get you then be able to do a spatial kind of analysis based on that, and we'll basically see how some of the that representation can help us understand more about different conditions be it infectious diseases, be it non-infectious diseases, and so forth. Then there's also the raster kind of data, which is basically, the pixel-based, and where each pixel kind of has a value representation information. But I kind of rarely use this type of spatial data. But of course, like I highlighted earlier, I will focus mainly on the vector type of data, which is in this case the polygons kind of perspective. So just taking that information, we now just try to bring the spatial kind of epidemiology kind of perspective. So spatial epidemiology, it's an area that have developed over the years, especially with the the increase in the geotechnology kind of aspects, and also GIS kind of technologies, which gave ability to to connect epidemiological events with the location where the individuals were, and this, of course, it goes back to John Snow basically, but the field has developed quite rapidly in the past 2 decades or so. Also, with the improvements in the computing aspects. So spatial epidemiology is concerned with the description, examination, spatial interaction of disease or disease risks, or health conditions, and focuses specifically on the spatial components in order to understand and explain why health and disease vary by place. And as statisticians, this is basically, or as biostatisticians, basically, one of the core reasons we do analysis is to try and help with the data-driven kind of decision making. So when it comes to having in-depth understanding, then the spatial epidemiology kind of helps us to then apply statistics at a level where one can easily make those kind of contribution. So in other words, we're looking at geographical variation in disease, health conditions with respect to the demographics, environmental, behavioral, socioeconomic, genetic, and infectious risk factors. And as you can notice here, it's rarely that you find a survey that collects genetic information. And it's also rarely that you find, all socioeconomic kind of variables collected in a survey. In other words, some of the socioeconomic variables can be in the data set, but there are some that may not be, in the data sets that we observe. And those contribute then to the spatial heterogeneity in terms of, the outcomes that we observe. In other words, we cannot explain certain aspects from our models, and the implication is that most of what is not explained goes into the error terms. So basically, there are quite a number of methods that we can use to explore this geographical variation and also to understand this geographical variation and its extent. And also, so this can be done through assessing clustering, for example, looking at whether there is any pattern that could be of interest, sustained kind of pattern, which is not random, And also you can look at, the spatial smoothing kind of approaching your kriging and so forth. Then there is spatial modeling, which is basically, the optimal way that we can understand, dynamics of outcomes with respect to given, different factors. So basically from several studies and systematic reviews, it's been highlighted that and it's been noted that several public health kind of problems, they tend to exhibit this spatial dependence. That is, you are likely to have spatial autocorrelation, spatial variability, especially when it comes to health conditions. You can think of your malaria, for example. Like in South Africa, you find malaria in Mpumalanga and parts of Mpumalanga, and also maybe parts of KZN and probably Limpopo. But it's not a widespread health problem in the whole of the country or in all of the provinces. So with that, there is that spatial kind of variability, and the autocorrelation part. You notice that in KZN and in Mpumalanga, it might be same areas that are on the borders for each of those particular regions. So there's that correlation between those particular areas, which will then have to be taken account of, especially if you are to get an understanding of this dynamic. Of course, our classical methods, they kind of ignore this particular component and assume independence, and then do the modeling and so forth. And that sometimes these problems are related to climatic factors that are generally of a spatially continuous nature. So with spatial modeling, you will be able to kind of explain in some detail most of these kind of aspects. So this then explains some of the limitations for the classical kind of methods. So the use of our classical statistical techniques to model spatial data generally leads to an overestimation of model parameters because of the the unmeasured kind of variables, which can then inflate some of the effects in the measured covariates that we add into the data. So although these models can help, but they lack adequate structure. In other words, the data generating process has a spatial component, which is ignored in most of the classical kind of approaches or methods. So because of that, we are not able basically to model the spatial variability of the data, which means we are using a slightly different data generating. We are estimating a slightly different data generating process than what has actually generated the data. So the implication for that is our learning also is going to be limited. It's going to be partial because we are learning from a structure which doesn't conform to the underlying kind of structure. So valuable information because of that will then be sent to the model error and cannot be used to explain the nature of the phenomena under the study. So with our classical methods, we ignore possible spatial autocorrelation, assuming kind of IID, and the goal basically for spatial epidemiology is to identify these spatial patterns and then trends in health and disease, and also to understand the relationships between these patterns and the underlying factors that contribute to them. So when it comes to some advantages that we can gain from using spatial analysis where it's supposed to be used, we can do descriptive analysis, which gives us some good visualizations, and also we can do spatial modeling. So evidence has shown that spatial models, they can help identify spatial patterns, clusters in infectious and non-infectious diseases. And a spatial cluster basically is an axis of events. That's basically just what we mean by the cluster. An axis of events or measurements in certain areas in geographic space, which may not be random. So in this case, I used DHS data basically from 2016 for South Africa, and just for illustrative purposes, I then estimated the proportion of hypertension in the different provinces, and you can see from here that there are high, prevalence of these NCDs or the hypertension basically in these particular provinces. That is the Northern Cape and Western Cape, and also the Eastern Cape is within the same range. Then we compare that to random kind of generated kind of prevalences. So when you have these prevalences randomly generated, then you are likely to see these kind of patterns, which do not have this kind of a pattern between regions. So you are able to test this statistically and get an understanding that this is not a random kind of pattern, but this is a structural kind of pattern. So these models also can help determine the factors that influences the different outcomes, and these factors may include your socio-demographic, your environmental, and also you can generate maps to visualize the distribution of either morbidity in terms of sickness, disease, or mortality of infectious diseases, and so forth. And this can identify critical points in spatial distribution of the kind of outcome. Then in terms of what kind of question can these kind of methods help to address? So we have this type of a question: does the spatial patterning of disease incidences or health conditions, in this case, the health conditions that we are interested in, does it give rise to the conclusion that they are clustered? In other words, there is a pattern, there is a structure that drives these clusters. And if so, are the clusters found related to factors such as age, relative poverty, or pollution sources? And these can be spatially associated. So you can see basically from this that our classical methods, they fall short in terms of addressing this type of a question. But further to just spatial modeling, there is also spatial temporal kind of analysis or modeling that has got additional benefits over spatial analysis, because this kind of considers both the spatial aspect or the spatial dependence of outcomes together with their temporal correlations, more like in a time series perspective. And we know that the time series data usually has got this temporal dependence, which is temporal correlation or autocorrelation, we call it, and makes it possible to observe the geographical and temporal kind of distribution of the phenomena through visualization of these epidemiological data that contain space and time information. So, so the importance includes identification of clusters, assessment of impact for environmental factors, enables evaluation of effective public health kind of interventions, provides basis for understanding complex relationships. And in terms of the approach, you are looking at looking at the framework for spatial analysis. So you've got attribute data, you've got feature data, and this attribute, spatial attribute data can be can be from GIS, database management systems, and then you have your feature data, which is your the other data set which contains probably your covariates, your outcomes, and so forth. So you can use mapping to visualize. You can use autocorrelation kind of analysis to explore the significance of these patterns, and then you can also use a regression framework to then get some in-depth understanding and also predict patterns. So in terms of mapping, this is the simple mapping, which shows which areas have got higher hypertension in this particular example. So just going to the models. So as we all understand from a statistics perspective, biostatistics, there are different outcomes that we are interested in at the end of the day. You have continuous outcomes, counts, binary, time to event. So spatial models kind of handles all these different types. Then we have these spatial models being extensions of the classical models. So for continuous kind of outcomes, we can think of geographically weighted kind of regression models. And then for other types, non-Gaussian kind of outcomes, we generally think of those from a perspective of conditional autoregressive kind of spatial models. And these are usually done to make inferences. Understanding this data basically, just like in any regression, you have got signal which you can predict from your systematic component and the noise. And the spatial kind of data, we have the signal which we can predict from the covariates, but we also have the spatial signal which we now add, and this is what gives the added value. In other words, if your data does not have a spatial structure, then you really don't have to use this more complicated kind of framework. So in this case, you can kind of specify that in terms of your mean function, which can be in terms of your covariates and so forth. And then you have the structural random effects, and then you have the unstructured random effects, which takes in the errors that remains or the residuals that remains after you have accounted for all these other aspects. So with the generalized linear models within the conditional autoregressive kind of framework, you have the link function, and then you just add the linear component, and then to the spatial random effects and the unstructured spatial effects. Then this can be extended to generalized additive kind of models where we don't assume a linear function or a linear effect for covariates, especially continuous kind of covariates. So we can have a component that takes care of the nonlinear effects and interactions, together with the fixed effects from the categorical kind of factors. And then we have the spatial component added to that. So this specification, I have used it, and many other different authors, have also used this specification, and it's also found, for the base X kind of, tutorials and methodological kind of documentation. So in this case, this is a specific case for binary outcomes, which can be measured as somebody has it or not. So this can be, the kind of framework that one can use. Where your spatial has got this structured spatial effect, unstructured spatial effect. And for all these, to account for the autocorrelation, we basically use the conditional autoregressive prior, in other words, within the Bayesian, full Bayesian inference framework. And the assumption here is that there is a smooth surface which captures the structured kind of spatial, effects for each particular region. So conditional on the neighboring kind of, or other random effects, spatial random effects, we can estimate the mean of a particular district or location effect by this function in a prior sense, and we estimate basically the precision by tau u in this particular case within a particular radius that is your delta I. And generally, the prior for this precision, we basically use a gamma distribution with this specification. So this has been suggested from different studies, but depending on the problem that one is working with, you can explore different priors, and in terms of how they influence your specific distribution of the random effects. So in terms of the spatial temporal, we then add the time aspect. In other words, the time at which the outcome was measured. So if it's in months, if it's been measured maybe over 12 months, so this would be the time in terms of 1, 2, 3, up to the 8 months or something like that. Then you can have the trend effect of the time, and also you can have the random effect of time that is associated with, or the random fluctuation of time that can be captured by this psi of 2j. And then the phi ij here captures the interaction between time and space. So that's the space-time kind of interaction. So these are the different model frameworks that one can think of when using when applying these spatial models. So this is just in terms of the applications where we have done some applications of these methods, and of course the COVID kind of taught us a number of things in terms of data sharing, in terms of how much studies can be done when data is collected properly, So in this case, we used the DATCOV, the data that was collected by NICD, and I worked with some colleagues at NICD to kind of apply these kind of methods. And the main goal for this study was to determine the district level kind of clustering in terms of in-hospital mortality, and the spatial effects and the variability of in-hospital deaths, and also to identify other factors that were associated with these deaths. There had been lots of other studies that had used logistic regression and so forth. Then this was just the mortality risk, across the districts, and we used the local indicators of spatial autocorrelation to basically see whether the observed clusters here with the very high, mortality risk were clustered or not. So we could see that there were spaces of red there which showed a high mortality risk, districts surrounded by other districts with similar high or similarly high, mortality risks. Then in terms of the modeling, we also added, a nonlinear effect of time in terms of the number of months that the data was collected in, and we could actually pick, the different, peaks for the pandemic, for the epidemic as well, the epidemic curves. Then in terms of age, the effect was actually, as age was increasing, the effect or the log odds of getting mortality was also going high. So we could actually pick those particular aspects. Then we used from the spatial model, we could determine that after adjusting for age, the time of observation for this, for the measured epidemic kind of rates, then we still remained with some spots that still had the high relative risk of getting mortality. So in this case, that showed there was still remaining some unexplained aspects. So we followed that by doing a spatial temporal kind of application, and now assessing the health systems kind of factors. And we could, of course, determine that in wave 2, that's where most of the mortality kind of risks were. And of course, in wave 4, there was, because that was vaccination had come in and so forth. But we could see, the districts that had high rates in Limpopo and also in the Eastern Cape. From the model, after adjusting for health systems factors and so forth, we could still have those particular areas which were highlighted there, and these in red here were the areas or the districts which had high probability of having risks that were above 1.5 relative risk. And this was obtained basically from fitting a negative binomial kind of model with the for count kind of data. And what this showed is this also correlated with the the COVID vulnerability index, which was done during the early days of COVID, which showed that these particular areas were vulnerable, basically due to their the socio-economic dynamics in those particular districts. So this was actually then captured from a modeling perspective, showing basically that there was those kind of challenges. Then we did another study with some colleagues from the US, also on COVID. But in this case, this was just to leverage, the spatial representation, visualization in order to make some statements. And in this case, we used the vector error correction models to fit the stochastic, patterns and trends of different variables that included anxiety rates, depression rates, to the different rates that were associated with COVID. And after fitting these models, we also did impulse response functions, which estimates whether the relationship is positive or negative after putting a shock on a particular variable. So we then so these are the kind of models that we fit for each of the different states, and then we picked the direction of the relationship, and then presented those relationships on the maps. The question was because the US said the polarity in that particular case, particular time, the red states, the blue states, and so forth. So we wanted to see, the question was, does the anxiety differ? Does depression differ? Does mental health kind of, aspects differ, depending on the state that somebody stayed in? So this actually showed that the second lag, was more relevant in terms of explaining, the influence on the particular outcomes. So we also did this for depression and for anxiety. Then for vaccination as well, which showed there was a negative, effect. In other words, the advent of vaccination reduced, the levels of anxiety or proportions of, anxiety in this case, and also depression, which is kind of, intuitive. Then the other application is within joint modeling, where you have two outcomes of interest. So this just illustrates, the kind of thought process. So this was a simple case with the rates of intimate partner violence. So you can see rates for men and for women. And the fun part was in the areas where there was the high rates of intimate partner violence against women, there was low intimate partner violence against men. So that's the kind of relationship that can be within in outcomes. But we then did that study and had so that was published as well. Then the last example that I want to share is on joint spatial modeling. In other words, looking at the same example that I had in the previous slide, but now jointly modeling the outcomes of interest, then to identify, shared risk patterns. In this case, we looked at hypertension and diabetes, which are known basically to share common socioeconomic, socio-demographic factors, anthropometric lifestyle risk factors, and we aim to, to jointly model the shared and disease-specific geographical variation of these two conditions. We used nationally representative survey data, and we did this within Winbugs. which implementing full Bayesian inference. And the shared patterns basically were modeled using this particular framework, where this is the joint model, where UIJ is the spatial kind of effects for a particular district J and disease K. So in this particular case, we have disease K being 1 or 2, diabetes or hypertension. And then these two models here, they then jointly model the shared risk, which is your UJ here, which is common in the two models. And using this framework, we actually were able to estimate and determine the areas where there was high shared risk for the two conditions. And from a public health perspective, you can then plan in terms of disease management, for these kind of cases. So so that's basically the presentation I had to share. And thank you again for the opportunity. And it leaves me just to acknowledge the SASA Spatial Statistics Interest Group, Pravesh and colleagues. Thank you very much. Over to you.
Okay, thanks, Dr. Maposa. So an interesting talk and a number of interesting examples. It would have been also nice to see the data sets that was used, or just some explanation of it. But I think time is a factor here. Perhaps if I can just check with anyone if they've got questions for Dr. Maposa. Please, if you can raise your hand with any questions. I do know we're running out of time, but if there's a few questions, we can still take that. Okay, Dr. Maposa, from my side, the data sets that we used, I know the first one on the data corp from NICD, but the one that you were using for USA, was that a survey that was done? And also the one for now, which country was it? There was a the third example.
For the last example.
Yes, for the last example.
Yeah. Okay. Yeah. So for the US data, it was data that was collected almost daily by the Delphi Research Group at Carnegie Mellon University. And this was collected and aggregated, by researchers from that university in collaboration with Facebook. So they put out their surveys through Facebook and collected the data. They had a dashboard which they were using to do that. So they collected the data on the questions like whether the respondent had reported feeling nervous. That's for anxiety, for example, feeling anxious or on the edge for most or all of the past 5 days. So it was more like every day they were calculating proportions of people that indicated And this was only in the US. So they would calculate proportions for that, and that the same for hypertension. And for HIV incidents, not HIV, but for COVID incidents, they used data from Johns Hopkins, who were collecting that information daily, and the same with the deaths kind of data as well. And of course, these were time series data, which were kind of autocorrelated, non-stationary and autocorrelated, and that's why we then ended up using the the vector error correction models to capture the relationships. Yeah.
Okay.
And the last one is basically a survey that was done in South Africa by the WHO STEPS surveys. Yeah, so that's the source of the data. It's a survey data set.
Okay, okay.
Yeah.
Okay, any questions from anyone? Okay, if there's no questions, Dr. Maposa, thanks very much for the talk. It was interesting, and I really appreciate you taking the time and presenting to the Spatial Stats interest group. I think there would be another talk that would be done shortly as well in a couple of weeks. And Inga would have sent out the message for that. So please do attend, guys. And until then, enjoy your time, and I'll see you again in the next session. Thanks a lot.
Thanks, Pravesh, and thanks everybody for attending.
Okay, take care. Bye.
Yes.